than experiments. So the objectives we're going to learn today are, we're going to learn that a sound wave is longitudinal. In addition, we'll look at the speed of sound and that formula. We will look at wavelength and frequency, how they're inversely related. We'll also talk about the Doppler effect. In addition, we'll talk about the amplitude of a sound wave, and then I'll end with something that I think is special. So let's get started. So you guys, if you take a Slinky, a lot of people have Slinkies already at home. So take a look at this, and when you think of a Slinky, a lot of times you think of it going up and down, like as far as going down the stairs, okay? If you do a wave though, when you think about a wave, a lot of times you think about it going this way. And I'll spread this out so it can move. So it goes up and down, okay? You're seeing that. That's called a transverse wave. This wave is perpendicular, so perpendicular to the wave, the direction the wave's going. But that's not how sound works. It's actually a longitudinal wave, which means its wave is the same direction as it travels. Okay, do you see that? It's parallel. They're the same direction. The way it's traveling as well as the wavelength are parallel. So that is a visual of a sound wave. Now let's look at experiment 14.1, which starts on page 344, and see if we can even see more sound. So what I'm going to do is I'm going to take a candle and I'm going to light it real quickly. Now when I light it, there's nothing special about that, right? We're going to light the candle. Now what you've already made is just taking a 2-liter bottle, cutting off the bottom, and putting saran wrap real tightly on it. So what I'm going to do, can you see, hopefully you can see that the light is on. Okay, do you see the candle? Now what do you think, what hypothesis do you think, if I tap this when it's over the candle, what do you think will happen? Okay, let's find out and see. Okay, did you see that? It went out. Okay, let's do it one more time. Let's light our candle. All right, one more time. Do you think that was just a fluke, or do you think it'll go out? Okay, and you see it's lit. All right, let's tap the bottom again. Went straight out. Now listen to this. Think about this. If the wave was like this, it would flicker, and then the candle flame would come back up, right? It would flicker because a wave would hit it, and then when it was down like that, the wave wouldn't go out. But when the wave is like it blows, the sound waves actually blow the candle out. All right, so that's one way to prove, right, that a sound wave is longitudinal. Now another way, if you take just a regular bowl, put saran wrap on it, okay, you see that? And then we're going to sprinkle just regular rice on top of it. Okay, so let's see, this is what we have. Okay, you see rice on top of my bowl. Now I've had mixed results with this experiment. All right, so what we're going to do is we're going to take a pan and we're going to take, it says a wooden spoon, I think any spoon. Now unfortunately you may not be able to tell what is going on. I'll bring this a little closer. Look closely, see if you can zoom in on the rice and see if anything happens. As I make a noise, let's see if we can see the sound waves moving the rice. And you have to kind of be loud. Wow. That might have been a bust. I didn't see it moving. But I bet it's no surprise that you've felt the beats, you know, well, if you've got beats on your ears, but no, a stereo, a speaker, you've probably felt that. So what happens if that noise is loud enough? What happens? Let's try it one more time. Let me do something metal. Let's see if we can do a metal. Here's a ladle. Let's see. And hopefully you can see, focus in on that rice, okay? And here we go. Ooh, are you seeing it? It is moving. This with a metal spoon in the metal pot, it is moving. So those sound waves, you're actually seeing sound waves. Those sound waves are actually moving the rice on this saran wrap. Okay, well, now how this tightly stretched saran wrap works is exactly how your eardrum, called the tympanic membrane, how that works as well. So it vibrates and then converts that movement through your cochlea, your inner ear, and then to your brain, eventually to your brain. Okay, so we've seen that sound waves are longitudinal. Now let's talk about the speed of sound. This right here is a required, and it's backwards. All right, well, you'll have to use your imagination. This is the formula for speed, okay, of sound. 331.5 plus 0.6, the temperature, okay? So you'll need to write that down when you're calculating the speed of sound. But also, sometimes you don't need to know the speed of sound, you need to know how far away something is, like lightning. And then, remember, we've already covered this, speed equals distance over time. Our triangle represents that formula, or the relationship between that formula. So we actually already have speed, and we know the time if like that lightning is 2 seconds away. So then you do your speed over your time will give you that distance. Okay, so hopefully that's fairly straightforward, and that you remember that. Now the experiment related to that is on page 347, experiment 14.2. What happens is speed goes much more slowly than light. So when you see something, that's almost instantaneous as opposed to when you hear it. So the experiment on 14.2 is get a friend, and we've kind of got a lot of time right now on our hands, so get a friend or family member. You guys separate, hit rocks, and see if you're seeing the rocks hit before you hear the sound. So once again, that's just talking about the speed of sound. Now it might be interesting if you did it when it was really cold or it was really warm to see the difference, right? Because the speed of sound is dependent on temperature. And remember, sound does not travel, it has to have a medium to travel. It does not travel in a vacuum. So space is silent, if you didn't know. Contrary to what some sci-fi shows might show you, space is silent. There's nothing for sound waves to travel through. Okay, now this is a fun experiment that you could easily do at home. Let's go ahead and move to page 353. It's experiment 14.3. So I've got these Coke bottles, and I've got 4 of them. You can do how many ever you want. And so let me show you. This one is filled up. You can see the water's right here. This one is a lot less. That water's right here. And then I'm doing less and less. This one's, less than half. And this is barely filled up, okay? Now, what do you think? Come up with a hypothesis real quickly of what do you think? We're talking about pitches. Now, we've talked about the wavelength and the frequency are inversely related. So the longer the wavelength, the slower the frequency, which will be a low pitch, okay? The smaller the wavelength, it's a higher frequency and a high pitch, okay? So let's experiment with this real quickly. I'm going to start with the glass bottle that has very little water. What do you think, high or low pitch? Let's see. Okay. Let's now, for totally contrasting purposes, let's take a look at the one with just barely any water. Now, when you're doing this at home, it's a little hard to actually get a noise from here, and anyone who has experience playing a flute or piccolo, you guys are experts at this already, right? I am not, so. I'm spilling water. Let's use the one where the water's here. So remember that tone, and let's see what the pitch is here. Let's do it back to back. Okay, now why did that happen? And let's do the math for grins. That's higher, and remember that water's here compared to way down here. Okay, let's talk about that real fast. So here you go, we have, and I just drew 3 bottles. What happens when the water is real low, it has an opportunity, those air waves, which are sound waves, have a lot of opportunity to make a long or a big wavelength, which is a lower frequency, which has a low pitch. Then this is medium, but look at here, this one that is filled up with water, it has a very small space. So it has a very small wavelength with a higher frequency and a high pitch. So these are inversely related. When one's big, the other's small. Okay, and we're familiar with inverse relationships when we talked about gravitational pull, gravitational force, or electromagnetic. As it got farther, right, the force got smaller. So we know what inverse relationship is like. All right, now the next experiment that we're just going to talk about, but I encourage you to do it, experiment 14.4, is talking about Doppler effect, okay? So you're used to this, whereas when an ambulance or a fire engine or whatever passes you, it gets a higher pitch as it comes closer to you, and then as it zooms off, it gets lower. You can also experience this on NASCAR. Okay, you're hearing a higher pitch, then a lower one, a higher pitch, and a lower one. Okay, what's making the noise is moving. So that will affect the pitch. Okay, so the experiment's kind of fun. Once again, you have a little bit of time right now. Have a driver in your house drive past you honking the horn. Okay, and you'll hear the pitch difference. Now you may want to warn neighbors or something that you're going to be honking the horn, because that's kind of annoying hearing that. But all in the name of science, experience the Doppler effect. Now the last experiment is experiment 14.5, and that starts on page 358. So this is talking about the amplitude of sound. So watch this. I'm going to grab a guitar. Okay, so based on what we just talked about, if I hold my finger here, and so I have this whole string, since this is my, what I'm going to vibrate, this is a sound. It's going to have a certain pitch. Okay, if I shorten that, let me bring my finger all the way down here, higher, lower, what do you think? You're right, it's going to be higher. Okay, so when the string is longer, I have a bigger wavelength and a lower frequency and a lower pitch. If I bring it down here, this is smaller and it's going to be a higher frequency and a higher pitch. Okay, so now what I'm going to do is I'm just going to stick my finger here in the middle, and I'm going to play a note. The amplitude doesn't change the frequency or the wavelength, but it changes the amplitude. So watch this. If I play the exact same note and I barely touch the string, now haven't changed this. The string hasn't changed in length, so the frequency and the wavelength don't change, but I'm going to really strum it hard now. Okay, so you've noticed the difference? Soft and louder. Okay, soft. Now louder. Okay, that's the amplitude. The frequency and the wavelength don't change, but that amplitude goes higher. Let me put, or bigger. So watch this. If you look at a wavelength right here, the frequency and wavelength haven't changed, so that means the pitch hasn't changed, but you see it's higher and lower. That means the same note is louder. That's what amplitude means. All right.